All right, so we discussed this theorem which says that so L over K be an extension and let alpha be an element in L, and alpha is algebraic over K if and only if the degree of the extension K of alpha over K is finite. The degree, if it is so, then the degree is given by the degree of its minimal polynomial of alpha, which is in K bracket X. So as we had seen that this is extremely useful theorem. So we defined L over K, an extension L over K is said to be algebraic if each alpha in L is algebraic. Okay. And so given an extension, we consider the set L sub A consisting of all those elements alpha in L, such that alpha is algebraic over K. And we have shown by using this theorem, we have seen that this is a field extension over K. And we have characterized finite extensions as follows. So L over K be an extension, then the following conditions are equivalent. Namely, L over K is finite, that means it is a finite extension. 2, so L is algebraic over K, and L is finitely generated over K. 3, so there exists finitely many elements alpha 1 up to alpha n in L, such that finitely many algebraic elements alpha 1 up to alpha n over L, such that L is equal to K of alpha 1 up to alpha n. These 3 conditions are equivalent, and so one special type of extension is when L is generated by a single element over K. Such an extension is called a simple extension. And we have seen another theorem which says that if M over L is algebraic, not necessarily a finite extension, and L over K is algebraic, then we had seen that M over K is also algebraic. So algebraic is well behaved. Okay. So M over K is algebraic. So this is what we had seen, and finally we have seen one theorem which says that if you have a ring homomorphism tau from L to L, such that tau fixes K, and suppose L over K is algebraic, then clearly tau is clearly this is 1-to-1. Any homomorphism between fields is 1-to-1. So if you have a ring homomorphism from L to L, which fixes tau, then tau is also 1-to. The main thing is that L over K must be an algebraic extension. So this is what we had discussed in the last class, and let us see. So because we were talking about the minimal polynomial, let us see how. So given a polynomial f of x over K bracket x, how do we know it is irreducible? So why do you want to do that? Because we were able to consider, so here if you see, so we were able to construct field extensions by considering the minimal polynomials of alpha. So if you know minimal polynomials, if you know irreducible polynomials in K bracket x, so you'll be able to construct field extensions. So in order to do that, first we need to understand how do how to test for irreducibility. Okay. So one of the famous tests is the Eisenstein's criterion, which is as follows: let R be an integral domain. And let F be the following polynomial: F0 plus F1x plus Fn x to the power of n, which is in R bracket x. This has the following property: F0, F1, Fn are relatively prime. I guess you need to know that we need integral domain and we need F2. Can you talk about? Okay, we can talk. You can talk about the notion of relatively prime even in an integral domain, because you have a notion of divisibility. So if you have two elements A and B, A is said to divide B if B is equal to A times C. But unless you have unique factorization, okay, let's take R to be an UFD. Okay. And we have F0, F1 up to Fn are relatively prime. But suppose P is a prime element in R, such that P divides Fi for each one for each I. So this means P does not divide Fn. P divides each and every coefficient F0, F1 up to Fn minus 1, but it does not divide Fn. And also, a P square divides F0. So we have these three conditions. F0 is, so this is a primitive polynomial. And secondly, that P divides each and every coefficient except the coefficient of the highest degree monomial. And also that P square divides a constant term. Okay. P square does not divide the constant term, sorry. And then F is irreducible in the R bracket X. So this is the Eisenstein's criteria. So suppose if it were the case that if the proof is quite easy, suppose it were the case F is equal to G times H, where G is written as G0 plus G1 and so on, Gr H to the power of R, and H is H0 plus H1x and so on plus Hs x to the power of S. But suppose these are not units. So that means F can be factored as a product of two polynomials. Both of them are not units. If R is equal to 0, then it follows that G0 would divide F, and in particular, it divides G0 would divide F0, G0 would divide F1, G0 would divide F sub n. So G0 is a common factor, and we have assumed that these are not units. In particular, we say that this implies that F is not primitive. But that is contrary to the first assumption. And therefore, the degree of Z0, degree of G is at least 1. And similarly, the degree of H is at least 1. Okay. So by H, so if you multiply these two, you multiply this G and H, you see that F0 is equal to G0 H0. Now we assume that P square does not divide G0 H0 by the third hypothesis. And therefore, let us assume that P does not divide H naught without loss of generality. Okay. Now, again, GRHS is equal to Fn. And why it doesn't divide GR? Now we have assumed that P does not divide Fn. In particular, P does not divide G sub R. So P does not divide H naught, P does not divide G sub R. Okay. So let I be the smallest integer or the least integer such that P does not divide G sub I. Okay. Then by what we had seen that I must be less than or equal to R because of this, and R is at least strictly less than N. This is at least 0. So this implies P divides F sub I. That is, P divides H0 Gi H1 Gi minus 1. We already know that P divides Fi. So Fi, so I is strictly less than N. And by the second hypothesis, P divides each and each and every Fi, where I is strictly less than N and greater than 0. So P divides Fi would imply P divides H0 Gi plus H1 Gi minus 1, and so on, plus Hi Z0. Now, we have already seen that so P divides Gj for j strictly less than I, because I is the least integer, such that P does not divide Gi. So for any integer j less than strictly less than I, P divides Gj. Okay. Now, so this entire thing is divisible by P. And we already know that this entire thing, which is Fi, is divisible by P. And therefore, this thing must also be divisible by P. But we had seen that P does not divide H0. So it follows that P divides Gi. But this is contradiction because I is the least integer such that P does not divide Gi. So this contradiction proves the theorem. So this is Eisenstein's criterion. And so, for example, the way to apply this is, for example, if you have x to the power of 5 minus 4x plus 2, as you can see, if you take p is equal to 2, then p divides, p does not divide 1, which is the coefficient of the highest degree monomial, and p divides each and every other coefficient. Okay, and of course, p square does not divide the constant term. So this polynomial is irreducible. So now if you say x to the power of n minus 2 over q bracket x, you can easily see that this is irreducible by taking p is equal to 2. So if you have a q, you can construct an extension q of alpha, which is of degree n, because this is the monic irreducible polynomial, and therefore this must be a minimal polynomial of alpha, where alpha is the root of alpha to the x to the power of n minus 2. So this entire thing is contained in C. So this always has a root in C, and therefore if you take one root, let us say alpha. So q of alpha would be an extension of q of degree n. And the degree is the degree of the minimal polynomial, which in this case is x to the power of n minus 2. So we had already seen that the minimal polynomial, another way to characterize is the unique monic irreducible polynomial. So if you know that it is monic and if it is irreducible, then we know that it must be the minimal polynomial, because this is the another characterization of the minimal polynomial. So now you see you were able to construct arbitrary large degree extensions, and therefore if you consider the algebraic closure of Q, so the degree of this is at least n for any natural number n. Therefore, in particular, the degree of the algebraic closure of Q is infinity. Okay. So there are other ways to construct other methods to check the reducibility. So which is so suppose you have the following polynomial. Yeah? This is by means of the substitution. Means of substitution. Suppose you have a polynomial of this kind, x to the power of 4 plus 4x cubed plus 10x squared plus 12x plus 7. Now we want to decide whether this is reducible in z bracket x or not, or q bracket x, it's the same thing by the Gauss's lemma. So so how do we proceed? Because there doesn't seem to, so you can't apply the isoextence criteria directly to this polynomial. Because if at all you have to choose a prime, you need to choose p is equal to 7. Because one of the conditions is that the prime must divide the constant term. But then it won't divide any of these coefficients here. So what is the way out? So instead, so what we do is we substitute y is equal to x plus 1. In this case, if you do that, that means x is equal to y minus 1. If you substitute this, f of x will be transformed to f of y, which is equal to y to the power of 4 plus 4y squared plus 2. So this thing is clearly irreducible in z bracket y. Now, there is a homomorphism from z bracket x to z bracket y given by ascending x to y minus 1. So this is clearly seen to be a ring isomorphism. Because if you have given a y, you can get x by x plus 1. Okay. And therefore, the kernel is also trivial, and therefore, it is an onto map, and therefore, this is an isomorphism. Isomorphism in rings. So, if this polynomial is irreducible in z bracket y, it is also irreducible in z bracket x. So, this polynomial is irreducible. Okay. So, the second property, the second way to do this is by localization, which is very interesting. So you consider Z, you consider the quotient map for a given prime P. You consider Z, you consider ring homomorphism from Z to Z mod P. So let us simply denote it by ZP. You take a polynomial f of x, you send it to f of x mod P. So for example, if you have f of f is equal to a naught plus a1 x plus a n x to the power of n, which is in z bracket x. And f bar would be a naught bar plus a1 bar x plus a n bar x to the power of n, which is in z. So some of these coefficients may turn out to be 0 because we are modding out by the prime p. Suppose we have this polynomial. This is called the localization principle, and we suppose a naught, a1 up to an are relatively prime. Suppose P does not divide an. So that is the condition. So what this means is, so if you consider f is a primitive polynomial, and suppose P does not divide an, this thing is, if f bar is is irreducible in ZP over ZP, then F is irreducible over Z. So checking this is very easy compared to checking this one. Okay. So this is the theorem. Suppose we take a primitive polynomial and mod out by p, the prime p, and suppose that p does not divide the coefficient of the highest degree polynomial, which is this an, and if f bar is irreducible in zp, then f is irreducible over z. So proof: suppose f factorizes as f is equal to g times h. And suppose g and h are not units. So as in the proof of Eisenstein's criteria, we can easily show that the degree of G is at least 1. And similarly, degree of H is at least 1. Okay. So, of course, the degree of G plus the degree of H is equal to degree of F. So since P does not divide AN, it follows that the degree of F bar is equal to degree of F. So this term won't become 0 and reduce the degree of F bar. So that is the reason why we assume that P does not divide AN. If P divides AN, this term will go to 0 and we are left with some AN minus 1 bar xn minus 1, and the degree of F bar would be at most n minus 1. So we make sure that won't happen. So degree of F bar is equal to degree of F. And of course, when you reduce this, because Z2 Z mod P extends to a ring homomorphism like this, it is also a ring homomorphism. So F is equal to GH would go to F bar is equal to G bar H bar. And of course, degree of G bar plus degree of H bar is equal to degree of F bar. But we already know that the degree of G bar is at most degree of G. The degree of H bar is equal to degree of H at most. So from this is equal to degree of F bar is equal to degree of F, which is equal to degree of F plus degree of G. Degree of G plus degree of H. So you have two numbers. This is less than, so this thing is less than this. This thing is less than this. So they must be equal. So this implies F bar is a non-trivial factorization of F bar in ZP. So what we are doing is to show that contrapositive. So if F is if F is reducible over Z, it is also reducible over ZP. So we have shown the contrapositive. So this seems very simple looking because everything is argued in terms of the degrees. This localization can be used to give an alternative proof of Eisenstein's criteria. This shows how useful localization is. So see how simple the proof of Eisenstein's criteria is. I'll go to proof of Eisenstein's criterion. Okay. So we had also recall what an Eisenstein's criteria is. F is A naught plus A1x plus AN x to the power of n. And we have assumed that this is primitive polynomial. That means the GCD of the coefficients is equal to 1. And also that P does not divide AN. So we had assumed that P divides each and every A naught A1 up to AN minus 1, and P does not divide A naught, P square does not divide A naught. So these are the conditions in Eisenstein's criteria. In particular, P does not divide AN. So we can use the localization principle, and F bar is equal to AN bar x to the power of n. F bar is equal to AN bar, and suppose F bar so we assume that suppose f is reducible, then we have f is equal to g times h. And we had seen that the degree of g and the degree of h are at least 1. And therefore, f bar can be written as a n bar times h to the power of n, which can be written as g bar h bar. Okay, so g bar h bar. And from this, you can easily see that g bar has degree at least 1, and the degree of h is at least 1. And therefore, g naught, which is the quotient, which is the constant term of g, is g naught bar is equal, g naught is 0 mod p, and also h naught is equal to 0 mod p. Why? Because f bar has no constant term, and you know that zp is a field. So zp bracket x is a PID. In fact, it is a UFD. In particular, it is a UFD. And therefore, G bar must be of the form x to the power of n something. This must be of the form x to the power of n minus m, with some other coefficients here, other units, some coefficients here. But we know from this that the constant terms of G bar and the constant terms of H bar must be 0. In particular, the constant term of Z bar is G naught bar, because you remember G naught is G naught plus G1x plus G r x to the power of r, and H is H naught plus H1x plus Hs x to the power of s. And therefore, G naught must be 0, must be congruent to 0 mod p, and similarly H naught must be congruent to 0 mod p. From this it follows that G naught H naught must be congruent to 0 mod p square. But this implies p square divides G naught H naught, which is a contradiction. Okay, so here we use the localization principle. If f is reducible over z, it is also reducible over zp. So, and its factorization can be obtained in this way. This is where we use the localization principle, and this actually gives us quite a sleek proof for the Eisenstein's criterion. All right. So let us see another example how localization is used. Let us prove that f is equal to x to the power of n plus px plus p square is irreducible in z bracket x. Now you can't use the Eisenstein's criteria here, because if you take the prime p, it divides the constant term. P square divides the constant term. Here you can't use the Eisenstein's criteria. Rather, you use the localization principle. First, observe that if alpha is a root of f in z, okay, alpha is a root of f in z, that means alpha to the power of n plus px plus p square is equal to 0. If you take mod p, this becomes alpha to the power of n is congruent to 0 mod p. This implies alpha is congruent to 0 mod p, because we are dealing with zp is a field, and therefore in particular it is a domain. So alpha is congruent to 0 mod p. So if that is the case, alpha is of the form k times p for some integer k. So if you substitute this in here, you will see that k times p to the power of n, which is equal to minus p times k times minus p square, which is minus p times k plus 1, k plus p. Is that right? H plus p square, p to the power of n, alpha to the power of n. So here we have p times k times p. So this is k plus 1, this is p square. So you'll have k, p to the power of n, p to the power of n minus 2 is equal to minus k plus 1, which is So we have to observe that alpha must be negative. Why? So if alpha is positive, alpha to the power of n is also positive, p to the times alpha is also positive, and p square is positive, and the whole thing is positive. It can't be zero. So alpha must be negative. So if alpha is negative, so this k must be negative. So if k is negative, we will have k is negative. We will have we have a minus k. Now you can say k is positive. We have minus k to the power of n. This is minus k. So this becomes plus k minus 1. Now you can see from this equation, this is an impossible equation. So it is minus k to the power of n times p to the power of n minus 2, which is k minus 1, which is impossible, right? So this has no solution. So if f is a factorization, if f has a factorization g times h in z bracket x, okay, then so this implies what does that mean? So this is an impossible thing. So there is no root in z. So this implies no root in z. In particular, if f is equal to g times h is a factorization in z, it follows that the degree of g is at least 2 and the degree of h is at least 2. Because if the degree is 1, that means you will have a root for f in z. Okay. So arguing as before that you will see that f bar is x to the power of n, and the rest of the terms is 0. F bar is 0. So this implies the degree of gi is congruent to 0 mod p. This is x to the power of n, x to the power of n minus 1 for n. This is my g bar times h bar. So this implies gi is congruent to 0 mod p for I strictly less than degree of g. And similarly, hj is equal to 0 mod p for j strictly less than degree of h. So that if you take the degree 1 term, this becomes g naught h1 plus g1 h0, which is p, but g naught, gi is congruent to 0, so this is congruent to 0. And this is also congruent to 0, this is congruent to 0, this is congruent to 0, this is congruent to 0 mod p square. So p is congruent to 0 mod p square, which is absurd. So this example shows that x power n plus px plus p square are reducible by using the localization technique. So we have seen substitution, Eisenstein's criteria, and localization to come up with polynomials which are irreducible. The next class we will see that we will see some Greek geometry that show that some constructions using the straight edge and a compass are impossible. Using the theory we have learned so far.